We mentioned several times that calcite is a uniaxial negative mineral. We said why, but we haven't demonstrated it. We'll explain now how that can be done. Note that the following procedures are not used or necessary on calcareous nanofossil observations. We'll only mention them to complete the description of the optical properties of calcite, and also to comment on the current use of the term isogyre to describe the extinction pattern of calcareous nanofossils. First, we need to change the observation conditions on the microscope by changing from cross-polars orthoscopic observations to a cross-polars conoscopic observation. The first is the one we have been using so far, in which the mineral is on focus. The second is a different method in which the object is out of focus and we need to insert an extra lens, the Amici-Bertrand lens that we referred in the first video. With this configuration, we obtain on a single field of view the effect of a cone of converging rays crossing the mineral coming from several directions at the same time, from the most oblique in the periphery of the field of view till the most vertical in the center. We also need to select a mineral that has its optical axis as vertical as possible. In terms of calcareous nanofossils, this would be equivalent to select a V unit. And this is the image we obtain by conoscopy. The black cross has obvious relation with directions of polarizer and analyzer. They are produced by the absence of those rays that are aligned with their directions, and so are blocked by the analyzer. The two arms of this cross are what in mineralogy is called the isogyres. They produce a single cross which demonstrates that the mineral is uniaxial. The center of the cross is the exact location of the optical axis or C-axis of symmetry for this specific crystal. Now we must keep in mind that in a conoscopy observation of a crystal, the orientation of the extraordinary and ordinary rays vary from one quadrant to another, like this image represents. Let's simplify the image. These are the orientations of the ordinary and extraordinary rays coming from all directions. The extraordinary ray vibrates along radial planes that contain the center of the cross or the optical axis. The ordinary ray vibrates along perpendicular tangential planes. Only their positions for the center of each quadrant are represented to simplify this diagram. Let's simplify even further and only consider in each quadrant the rays that vibrate in the same direction of the gypsum plate. Now, when we insert the gypsum plate, we obtain a yellow retardation color on first and third quadrants, and a second order blue on the second and fourth quadrants. Based on what we referred earlier, yellow on the quadrants that have the extraordinary ray oriented northeast-southwest means that retardation diminishes. So, the calcite extraordinary ray has to be the fastest one. On the other hand, blue on the quadrants that have the ordinary ray oriented northeast-southwest means that retardation increases. So, the calcite ordinary ray has to be the slowest. In conclusion, we can finally reconstruct the ellipsoid of velocities for calcite, which in turn corresponds to an oblate refractive index ellipsoid characteristic of a uniaxial negative mineral, as we said at the beginning of these presentations. To finish, and although these two images look alike, the term isogyre to describe the black cross that many calcareous nanofossils display is not formally correct. Can you enumerate the three reasons why? First, the isogyres are obtained on conoscopy observations to determine the optical signal of a mineral. In these conditions, there is an additional lens inserted in the microscope and the object is out of focus. The extinction cross on calcareous nanofossils, on the other hand, are obtained without the Amici-Bertrand lens and with the specimen in focus and in orthogonal observations. Second, the two isogyres crossing each other are obtained from a single crystal section. The extinction cross on calcareous nanofossils, on the other hand, result from the combined extinction pattern of multiple crystallites that compose them. Third, to obtain the isogyres, the mineral must have its optical axis vertically. The extinction cross on calcareous nanofossils, on the other hand, are obtained with R units, not with V units. Sorry, Jeremy, but we need to find a new term for the two arms of the extinction cross of the calcareous nanofossils. Something like extinction lines seems to me much better. Now that we covered all main crystallographic and mineralogical properties of the calcite needed to correctly interpret observations under a petrographic microscope, you're ready to start learning the morphological features and the taxonomy of calcareous nanofossils. Good work, have fun, and see you in one of our next INA meetings. Don't know what INA stands for? It's the acronym for International Nanoplankton Association. Join us, we are eager to welcome you aboard.